Okay. So next one, we are going to see about Sensistor. I told you one more device you have, thermistor and sensistor are opposite in working. Okay. So here I am going to sensistor. Sensistor is a device which is represented by RS, which is going to have positive temperature coefficient. It's going to have positive temperature coefficient. So the temperature, as the temperature is going to increase, the resistance value is also going to increase, positive temperature coefficient. And since I connected thermistor across R2, I'll be connecting sensistor across R1. So RS is connected across R1, parallel to R1, between VCC and collector, base VCC and base. Okay, so you know that in a sensistor, the resistance will increase with temperature. So it is a positive temperature coefficient device. So the resistance will increase with temperature. So for example, consider the temperature is increasing. So when the temperature is increasing, this RS will increase. So when RS is increasing, the parallel combination of R1 and RS will also increase. Okay, this parallel combination will increase. Okay, and hence the BBE will decrease, reducing IC. So this is how you are going to keep a check on the collector current. So when this resistance value is going to increase, the base voltage VBE will decrease. When the base voltage is decreasing, the current flowing through the base will decrease. When IB is going to decrease, IC is also going to decrease. So it is going to be a feedback mechanism. Just like how you drive a car in a road and suddenly you see a speed breaker, automatically your mind says you have to put a brake. So that is actually happening, right? Same way. So here I am going to put a sensistor parallel to R1. So as the temperature is going to increase, IC will increase. But effectively R1 parallel to RS is going to be large. When R1 parallel to RS is going to be large, when the resistance is large, the current is less. So IB is less. When the base current is going to be reduced, effectively collector current will also be reduced. So as I said, it is 2 milliamperes. Because of variation in temperature, it has gone to 4 milliamperes. And because of the action of sensistor from 4, it will again come back to 2 milliamperes. So this constancy in the collector current value is always maintained because of this sensistor. The thermistor, it's a negative coefficient, temperature coefficient device, which is connected across R2. Sensistor is a positive temperature coefficient device. It is connected across R1. It is connected across R1. So this reduced IC will compensate for the increase in IC naught, VB, and beta due to temperature rise. So whatever way your collector current is increasing, that much amount it will again reduce and come back to its original value when it is increasing because of the variation in IC naught, VB, and beta. So for these three parameters, I told you they are very, very important parameters because these three will depend on temperature. Accordingly, you can understand these three parameters only. We have designed the stability factors S, S dash, and S double dash. So these three parameters play a very, very crucial role in deciding the performance of your BJT. Okay, so any queries you have in sensistor based compensation technique? See, it is just you have to draw the diagram and you have to say what is a thermistor or sensistor, how it is working. And when you put that in a biasing circuit, you should say when the temperature is going to increase, how the collector current is maintained constant. That's all. That is what you have to explain when these type of questions are asked in your exam. Explain about thermistor based bias compensation or explain about sensistor based bias compensation. It's going to be very, very simple. You have to explain the logic.